Okay, so now we're going to do the variance of the binomial distribution. The variance of the binomial distribution. So we will quickly use this as an opportunity to recap the binomial distribution. And because we need to recap the fact that it is the sum of n independent IID Bernoulli distributions, i.e. n independent and identically distributed Bernoulli distributions. Okay, so if we take as our abstract probability space something like, say, flipping a coin n times. So we flip a coin n times, flip a coin n times, and we put every possible outcome of that experiment into this abstract probability space here. So, for instance, we would have heads, heads, tails, tails, heads, heads, and let's say n was equal to 7, i.e. you'd flip it 7 times, and this is what you got. So on the first one you got a heads, on the second one you got a heads, third you got a tail, etc. So every possible outcome that you could possibly get would be in there, and the number of possible outcomes are you could get heads or tails on the first one, you could get heads or tails on this one, so it would be 2 to the power of n would be the total number of possible outcomes on here. So we devise a random variable on this, which is x, which is going to map you onto the real numbers, and it's going to map you onto 0, 1, 2, all the way up to n. And the way it's going to work is that x is going to map an outcome s, so this is an outcome, it's going to map it onto the number of heads you get, So in this case, you'd count up the heads, you get 4 heads in this, so you'd map this onto 4, number of heads you get. So you could get 0 heads, which is the case that you get all tails, or you could get n heads, which is the case that you get all heads. So that's a random variable. Okay, and basically, this will, well, it will have certain probabilities. There will be a probability that you get 0, which will be the probability that you get, well, there's only a single outcome whereby you can get all 0 heads, which is that you get all tails, and the probability of that single event that you get tails is 1 over 2 to the power of n. So that's pretty unlikely. But each of them will have a probability, and it will inherit the probability from its inverse image in here. So if we look at the set containing the singleton little x, then there's a set in here which is x inverse of the set containing little x. In this case it was the set containing the outcome tail, tail, tail n times, but for some of these old more complicated ones there'll be a whole loads of different outcomes in the inverse image of that event. Okay? So now what we can do is we can define more random variables. We can define a random variable x1, which is going to map s, and it's going to map it onto either 0 or 1. And it's going to map it onto 0 if you get if first flip is a tail, and 1 if the first flip is a head. And then we can define x2, which is going to map, so that's perfectly well defined. Let me just discuss this one before I define x2. So in this case we'll map it onto 1 because you've got a head first. So for every single outcome, in your first flip you either got a tail or you got a head, and it will be ascribed in either a 0 or a 1, depending on which it is. Now I should have said something right at the start of this. I should have said that the probability of getting a head is p, and the probability of getting a tail on any flip is q. So this random variable here, x1, is going to be Bernoulli distributed p, because the probability that you get a head on your first flip is going to be p, and the probability that you get a tail on your first flip is going to be q. So that indeed is going to be distributed Bernoulli p. So x2 is going to map s onto either 0 or 1, and it's going to map it onto 0 if the second flip is a tail, and it's going to map it onto 1 if the second flip is a head. And similarly, this is again distributed Bernoulli p, basically, because the probability of getting a head on your second flip is going to be p, and the probability of getting a tail is going to be q, because the probabilities remain the same. And we can go on like this, so you can find more random variables. You can go on and define all the way up to xn, which is going to map s, an outcome, onto 0 or 1, and it's going to map it onto 0 if the nth flip, so the final flip, is a tail, and it's going to map it onto 1 if the nth flip is a head. Now these turn out to, and again, xn is going to be distributed Bernoulli p. So all of these random variables, x1, x2, through all the way up to xn, are all identically distributed Bernoulli p distributions. That's how all of them are distributed. It turns out that they're also independent, and the intuitive reason for that is that what you get on the first flip does not affect what you get on the second flip. If you want, you can write down, you know, n is equal to 7, and you can go through every single equation and check, if you so wish, that it is that every single relationship for independence does indeed hold, and you will find that yes, these random variables are perfectly independent. So we have n independent and identically distributed Bernoulli p random variables. Okay, now note that x, this random variable that we originally started off with, x, which is going to ascribe to every outcome the number of heads in the total number of heads, is going to be equal to x1 plus x2 plus all the way up to plus xn, i.e. this is going to be 1 if you get a head in your first flip, this is going to be 1 if you get a head in your second flip, etc. And it's going to be 0 if you get a tail. So the sum of this is going to add up to the total number of heads you get in your overall outcome. So indeed, it is true that this sum is going to have the same value as x, so it's going to be the same random variable. Okay, so now what we can say is that if we want to work out the variance, because they are all independent and identically distributed, we know that the variance of x is equal to the variance of x1 plus the variance of x2 plus all the way up to the variance of xn. And we know that all of these are distributed Bernoulli p, and we showed in the previous video that their variances is going to be pq. So we're going to add up pq plus pq all the way up to the nth one, which is going to be pq. So overall the variance is going to be npq, and occasionally you'll see this written np1 minus p. In fact, actually that's more common to see it written like that. So that's the variance of a binomial distribution. Now, that isn't a very satisfying argument for why this is true. It's very nice and simple, but I did not prove the crucial step here. I did not prove to you that the variance of x is equal to the variance of x1 plus the variance of x2 all the way up to the plus the variance of xn. So instead I want to give you another argument for why the variance of a binomial distribution is equal to this, and in a way that will help you to believe that the variance of x is indeed the variance of x1 plus the variance of x2 plus the variance of xn if x1 through xn are all independent and identically distributed. Well, are all independent is the key statement. Okay, so let's calculate the expected the variance of the binomial distribution in another way. So we can do it through another way, because the variance of a binomial distribution x is defined to be equal to the expected value of x minus the expected value of x squared. Now we know that it's the expected value of this random variable here. Now we know that the expected value of x is equal to np. Okay, and we'll continue this video in the next discussion in the next video.